recording now. Yay, we're recording. Yay. All right, so, oh, Jesus. So we're going to do the quantitative module. And the thing about the quantitative module is it's essentially statistics. We give it the fancy name of quantitative so we don't scare people away. How many of you are confident in statistics? How many of you are definitely not confident in statistics? All right, that's good, that's good. Because I decided to make this very, very basic, and I'm going to gauge the difficulty as we go forward based upon student responses. And the thing is, I don't really expect you to be statisticians at the end of this. I just want you to be able to read a paper and to extract the relevant information and to be able to critique to some extent whether the choices made in that paper were appropriate. And hopefully there'll be some elements of this that you will want to add to your thesis. And increasingly more people are doing qualitative theses, and that's good. But in my opinion, to be competitive in the world today, you need two sets of skills. You need communication, you need analysis. Communication is this. It's also a lot of writing, languages, and analysis is this. Is statistics or qualitative analysis or econometrics or something of that nature. The ability to look at data and extract wisdom from it. So let's move forward here. So what I want is just to get you up to speed on the very basics of basic statistical basics. And by the way, my French is atrocious, so I'll speak as slowly as I can in English, and if your English isn't great, then stop me and I'll try to repeat myself. And I'm going to try to give you a taste of the advanced methods as well that you may want to apply to your thesis. But again, don't freak out if it's above you. This is mostly for intellectual satisfaction, right? And hopefully we'll get you to a place where you can do some basic data analysis yourself as well. The way I've broken down the sessions, there are 6 sessions in total. That should be 6 over here, sorry. Right here, 6. This should be 6. Today is an introductory session. I'll try to catch you up as much as I can on the theory of statistics. And then the other sessions are here. We've got a double session here because I've got something to do that week, the following week, so I won't be around. And I've broken down the content in this way here. So today is all this sort of sounds boring, but it isn't. To me, this is the most important part, the interesting sort of philosophical aspects of statistics. And then next session, we'll go into actual doing tests. At the end of this, one of the ways that I gauge success in teaching statistics is if I present you with a research question, you're able to give me some options of the test that you will choose to analyze the data. You don't have to be entirely right, just be on the right path. For example, is the data continuous? Is it categorical? Is it parametric? If so, here are my choices for tests that I might apply to it. Here are the things I can do to clean my data. I can check for outliers, I can check for missing data, etc. If you take that away from this, I'll be happy. And because I'm supposed to also evaluate you, I had to throw in some assignments. But frankly, in a graduate class, evaluation is kind of meaningless to me. Like, I think we're all here to learn, right? So don't be afraid of the assignments. Everyone's going to do well if you make an effort. Right? And we'll modify the marks if everyone does poorly. So don't freak out about this. I just want you to learn as much as you can. Essentially, there are 2 data analysis assignments. One in which I will tell you just do these analyses and give me the results. And the other in which I will give you a data set with some questions. And you will figure out how to interrogate the data set and answer the questions. As simple as that. And hopefully, the next couple weeks, how that unfolds will be clearer to you. Now, this university loves SPSS. There are many statistical packages out there. SPSS is not the industry standard. The industry standard is probably something called SAS, S-A-S. SAS is used by all the big companies in the East USA that do big data analyses and things like that. Increasingly, the industry standard is becoming something called R. R is free to download. It's open access. SAS is not. Another competitive piece of software is called Stata, S-T-A-T-A. That's not free either, but it's rising in popularity. This university loves SPSS. Why? Because we bought a license for SPSS. That's the only real reason for it. So I will teach you the basics of SPSS. I didn't reserve lab time for you because I want to make sure that we get as much this as possible. So instead, I'm going to ask you to get a copy of SPSS. Now, you could drop on 10 bucks and buy it. I don't recommend you buy it. I shouldn't be recording this right now because I'm going to tell you to do illegal things in a moment. But we'll pretend I didn't have this conversation. There's a free evaluation version you can download. That's fine. It expires in like 2 months or something, and you only have me for 6 sessions, so why not? There is an open access version called PSPP, SPSS, PSPP. Clever? Okay. It does exactly the same thing, but it's run by an organization of volunteers, so it's a little clunkier, and it may be buggy, but it's completely free and open source. Now, there's another option. This will not appear on your slides. This is just this because this is an illegal option, because I'm that guy. I have a download site where I keep my illegal download software. If you go there, you write that site down right now. Try it down. Right? download.mylastname.com/download.html. And if you go there, everybody got that? Okay. If you go there, you get this page, which is my personal download site, which claims these are all evaluation copies of software. They're not evaluation copies. They're the full versions. Okay, that's a secret between me and you, and don't tell anybody else. And this is only for Windows-based machines. If you have a Mac, you're out of luck. I'm sorry, you got to go the other paths. But if you have a Windows-based machine, there's a Mac version here. Number 2, I recommend, if you download it and follow the instructions carefully, you can install a full, illegal, but non-expiring free version of SPSS. That's the last time I will say that. And if you want to ask, I didn't say it. So moving on now. Any questions about illegal downloads before I move on? No? Okay.
Sorry.
Yes. Yes.
I have SPSS adapted the last version.
Okay, that's fine.
That's okay?
Yep, that's great, yeah. Because we're doing very, very basic stuff, so any version will work. And frankly, if you don't want to use SPSS, if you want to use something else, that's fine too. Okay. It's just that I won't be teaching other software. If you want to do your assignment using Excel, you can do that if you want. Okay, but...
Okay. Another question.
Yep.
I used it to use EpiInfo.
Mm-hmm.
It is also...
Yeah, I know EpiInfo well. Yeah.
Yeah.
EpiInfo is good. EpiInfo is not powerful enough to do most analyses.
Okay.
But you can try it. Right? It's free as well. EpiInfo is a free piece of software produced by the CDC to allow public health units around the world to collect health data and do analyses on the run. It's really good for designing surveys and intake forms and do analyses in the background. But it doesn't do multivariable stuff well. It doesn't do regressions well. But you can try it. My personal bias is don't spend money until you absolutely have to. Be as free and cheap as you can until there's no other option. Okay, so try the EpiInfo, try the Excel. But if you want to try SPSS, get the evaluation copy and play along. Okay, any other questions about software? Excellent. When we talk about statistics, it's a scary word, I know. And historically, it's been very interesting. So the word comes from affairs of the state, because the original statisticians were people who collected data about the people to report back to the government. So back in the Middle Ages, we sent out people to count how many houses there were, how many cows people have, how much money they have stashed away, and we know how much to tax them. So affairs of the state became statistics. And early on, the best statisticians were astronomers. So many of the techniques that I'll be showing you were actually invented by astronomers. Astronomers were hired to be the official statisticians in many of the European royal nations, and we've inherited their techniques and their terminology. Now, before I move on, there are 2 ways of thinking about statistics. If I ask you, what are the chances of me getting a heads if I flip a coin? Okay? Versus if I ask you, what are the chances that my dog actually secretly hates me? Well, 0, because my dog loves me. Right? But they're kind of different, right? If I'm saying, I'm flipping a coin and I'm going to get a heads, what I'm really saying is, if I were to flip a coin a billion times, how many times would it be heads? And if I do it a billion times, exactly half of the time it would be heads. So my chances are 50%. If I say my dog secretly hates me, well, I can't ask my dog a billion times if he hates me. I can't get a billion dogs and test this, you know? It's not a realistic situation. So that's two different ways of thinking about the same question. One of them is actually doing an experiment of repeating something over and over again. The other is expressing how much confidence I have in an estimate. We have two words for this, right? Frequentist and Bayesian. Frequentist is how we usually think about statistics. That is, if I were to repeat the experiment a billion times, what are the chances things will happen? A Bayesian method, this comes from a man named Bayes, who wrote Bayes' theorem several hundred years ago. This is now the ascendant way of thinking. But this is not what I'll be teaching. This is now what everyone does, but no one teaches. Everyone teaches that. And the reason everybody teaches that is that this has only come into play because we have computers now. Because Bayesian methods involve estimating. I think my dog loves me 30%. Right? Then I'll do a test and say, actually it's 35%, actually it's 33%, until I get it down to an exact number. So with the computer revolution of the last 25 years or so, Bayesian methods have become enormously powerful. And if you go on in your career, let's say you want to become an epidemiologist, as I hope you do, because I'm an epidemiologist, and it's the science of the gods, and so much opportunity. So the best, most marketable epidemiologists are Bayesian specialists now, in my opinion. And in Canada, there may be 12 people who can do Bayesian statistics really, really well, and they're very marketable. So keep that word in the back of your brain. You may read about it as your career unfolds, but that is not what we're teaching. We're teaching this thing where we will pretend to have done a billion experiments, and you'll see how that plays out as we make diagrams and p-values and confidence intervals. All that stuff comes from frequentist perspective. Okay. So that's the last I will say of Bayesian methods. I'm moving on now. No more Bayesian methods. Next thing I want to review with you are the types of hypotheses. Now, hopefully all of this is review for you. If it isn't, stop me, I'll slow down. Because I have a lot of stuff to cover today, and if we don't get through it all, that's fine. We'll do it later. Okay. So, but some words I don't know why this is not working. Some words that will come up in your readings are null hypothesis and alternate hypothesis, right? The null hypothesis is the thing that we are always testing when we do statistics. And this is important philosophically, which is why I'm going to spend some time talking about it, because I can teach you, hey, here, do the math, or I can teach you the philosophy underlying why we do the math. And I think for graduate students, that's more important. So the null hypothesis is our default state. Anytime we go into an experiment or a test, we say, well, there is nothing here. There's nothing extraordinary here. Right? That's the baseline state. I'm hoping to find sufficient evidence that the alternate hypothesis is true, that something is here. And I've used the word guilt here, and I'll show you why guilt is in play. So I'll say it again. The null hypothesis is where we begin. If I'm testing whether a drug works or not to cure headaches, right? I begin by saying the drug does not work. Now let's do an experiment to see if I can get enough evidence to convince me now that the drug does work. So the question now becomes, how much evidence do I need? And that's where statistics comes in. We try to figure out at what point is the evidence sufficient to topple my paradigm and move me from the null state to the alternate state. Just remember, the null says nothing's going on. Right? We write it this way. H sub O and H sub A, sometimes H sub 1 people use. So in the notation in textbooks, and I'll be showing you, H sub naught means null hypothesis, H sub A means the other thing. So we want the other thing. We don't want the null, but we begin by assuming the null. Okay. One way to think about this is in a court of law. So let's say somebody has been charged with murder. We have a jury, we have a defense, we have a prosecutor, and we have someone who's on trial. Okay? So the way that the courts of law work in the Western world is almost the same as the way that the hypothesis generation works in statistics. In the Western world, you are innocent until proven guilty. Okay? So the null hypothesis is that you are innocent. There's nothing going on here. This man is fine. He didn't do anything bad. We're looking for sufficient evidence to topple the null and to convince us that in fact he is guilty. And the jury's job is to assess that evidence and to make a determination. So a common strategy is for the defense lawyer to introduce reasonable doubt to the jury. So how much doubt is reasonable to topple that expectation? Now I'm going to put a seed in your brain. This is how we get p-values. P-values is how much reasonable doubt is sufficient now to topple the hypothesis. So the burden is on the prosecution to prove someone's guilty. If you're ever charged with murder, a fine defense is to show up and say nothing, because you're assumed to be innocent. It's the other side's job to prove that you're guilty. So the experiment is our attempt to prove that he's guilty. The experiment we do comparing this drug to see if it cures your headache enough, that's the prosecution saying, this drug is guilty of curing headaches. Okay. So the null hypothesis, the defendant is not guilty. The alternative, the defendant is guilty. Okay. If the jury decides that he is guilty, they have rejected the null hypothesis. By the way, philosophically, they can never accept the alternative hypothesis. Right? They say they failed to reject the null. This is an important philosophical point. And this is something that statisticians debate all the time. So let's go over this slightly. If you're on trial for murder, the jury may say he is not guilty. They will never say he is innocent. Do you see the distinction there? There's a difference between being innocent and being not guilty. Not guilty means we didn't have enough evidence to show that he's guilty. Innocent is a positivist statement saying, this man is innocent, get him out of here. This is a travesty of justice, whatever it might be. Usually is the case as well, we think he actually did do it, but we haven't got enough evidence to show that he did it. The same in statistics. We never accept the we never accept the null. We always fail to reject the null. And I'll say it again. It's early in the morning. My brain is still trying to sort through the day. We never accept the null. We never say that he is innocent. We always fail to reject it. Yeah. Now, some statisticians will actually say in passing, I accept the null hypothesis. That's not correct. You fail to reject it. The same way we never say a man is innocent. We say we fail to prove that he's guilty. Okay, done. That's the last I'll say about that. We can move on now. Okay, well, that's not the last thing. So now there are 4 possibilities in that setup. So let's say he really is guilty. He really is guilty. But the jury found that there wasn't enough evidence to find him guilty. They acquitted him. That's a wrong decision. Let's say he is not guilty and the jury convicted him. That's also a wrong decision. So of the 4 possibilities, there are 2 right decisions and 2 wrong decisions. All right? And we like to think about these wrong decisions as types of error. Type 1 error and type 2 error. Type 1 error is when the man really is innocent, but we convicted him anyway. And type 2 error is when he was actually guilty and we let him go. What do you think is worse? To commit a type 1 error or a type 2 error? Think about it in terms of the law. Is it worse to convict an innocent man, or is it worse to let a guilty man go free? What are you saying?
I'm saying type 2.
Think type 2 is worse? Okay, any other?
It's not simple. It's not. You can't. It depends on the crime.
Does it depend on the crime? The law would say otherwise. So under Western law, there's a philosophy built into this. The reason that the threshold for proof is so high to meet is we make it very, very hard to convict. right? So the burden of proof is very, very high because we want to minimize type 1 error. It is atrocious to put an innocent man in prison, right? Now, we can disagree with that philosophically, but that's the choice that Western society has made. This is not a law class, a stats class. I don't want to get too deep into that. But I mention this because the same philosophy applies to statistics, right? So think about it in terms of a drug now. If we're testing whether a drug works or not, if you're a drug company, you've been hired to test whether this new drug actually cures headaches or not, is it worse for you to say that a drug that doesn't work actually does work? Or is it worse for you to say that a drug that does work doesn't work? The first one is worse, absolutely. Because you don't want bad drugs out there not doing anything. This happens all the time. We have great drugs that don't make it to market because they don't quite make the threshold to reject the null hypothesis. Right? So in fear of committing a type 1 error, we make a lot of type 2 errors. The two are balanced out. To minimize one, the other has to go up. That's the way it works. Okay, so do consider that. And if you take nothing away from this class, think about type 1 and type 2 errors in your life. It'll come up a lot in science. Yes?
I'm sorry, maybe I'm really confused, but I thought that we couldn't accept the null hypothesis.
That's right.
So what if it says accept not hypothesis?
Oh, that's right, sorry. Yeah. Yes.
So it should say...
We say fail to reject. It's just that this slide, I stole this from a statistician friend of mine who does not use that language, and we fight about this all the time. Okay. And in a previous lecture, another lecture, I used the slide to sort of pick on him a bit, but I forgot to change that. Yeah, good point. All right, so that's that philosophy. So again, we are looking to minimize type 1 error at the expense of making type 2 error a little more likely. Right? So again, type 1 error is convicting an innocent person. That's like saying the drug doesn't work, but we think it did work. You don't want that. You don't want drugs out there that aren't working. Type 2 error is you acquit a guilty person. Happens all the time. OJ. Right? That's like saying the drug actually does work, but we don't think it does. So again, we have a lot of drugs sitting in the storehouse that probably do some good, but they're not sufficiently good to make it to market. Okay, so that's the background philosophy. Now we're going to cover just some review of your stats from high school to undergrad that you probably did not learn well because you weren't taught as charismatically as I'm going to teach it. Easy stuff. Okay, there are two kinds of variables. By the way, a variable is just a placekeeper for a value. Okay, so your height in centimeters, what does that measure? It measures how high you are off the ground. Okay? Your height is not actually a physical construct, it's a label for describing something in the physical world. That's another philosophical angle. But there are two different ways of expressing quantity, continuous and categorical. We also call categorical stuff discrete. So continuous is it's like a flowing river, right? There's value in between the numbers. Your age is continuous. Maybe you're 25 years old. Right? Maybe you're 25.1 years old. Maybe you're 25.12 years old. I can go infinitely precise in your age because it's continuous. It's like water. I can subdivide it infinitely. Categorical, I can't subdivide. I can say, what province were you born in? Is it Quebec? Is it Ontario? Is it Nova Scotia? There's nothing in between. Or I can say, what is your age group? Are you over 25 or are you 25 and younger? There's no in-betweens. So a lot of people who aren't well trained in statistics, when I ask them to develop a survey, for example, they will ask all kinds of categorical questions, like, hey, ask the respondent about their age. They'll say, oh, I'll choose under 25, over 25, under 50, whatever it might be. Is that useful? I would argue no. There's more information to be had in continuous stuff than there is in categorical stuff, but we'll get there. Right? Let's keep in mind, though, there are two different types of variables, continuous and categorical. And amongst categorical variables, there are a variety of types. The most common is dichotomous. You can ask, what is your sex? Well, historically, male, female. You can ask, are you a student in this class? Yes or no. In surveys, a lot of yes-no questions. These are dichotomous. I can dichotomize. To dichotomize means to take something that was not to and make it to. Extremely common. So I can convert age, which is a continuous variable, to a dichotomous variable. So if I know that you're born in 1985, then I know that you are, what was that? I can't do the math this early in the morning. 25, 15, 20, 35, 34 years old. Okay? But I can also say, are you under 40 or over 39? And use that data to convert. If I go continuous to dichotomous, I can't go dichotomous to continuous. If I know that you're over 40, I don't know that you're 42. Right? So when we go in that direction from continuous to categorical, we lose information. So another thing I want you to take away from this is how we gain and lose information as we do analyses. It's a mistake very commonly made with people who don't understand numbers well. We lose wisdom as we go. So I put a paper on Brightspace. You may want to read it. It's entertaining. So it just goes through the cost of dichotomizing continuous variables. If you're looking for some more background stuff. Okay. Now, since we're on the topic of how to organize numbers, or what the nature of variables are, I want to introduce this idea of levels of measurement. There are 4 levels of measurement. Has anyone heard of these before? The levels of measurement. It's 1, 2, 3. Good. Okay, most people have. Excellent. This is a good review. Okay. The levels of measurement are nominal, ordinal, interval, and ratio. It's not that important. It's kind of important, right? The most important aspect of it is this is the best one, and this is the least best one. Almost everything you'll find in survey work, in the work done in health sciences, a lot of it is nominal. It should be ratio. Okay, and here's how it works out. Nominal means name, like no, right? It's just a category that has no intrinsic mathematical value. If I ask you what country you were born in, I can say Canada, USA, France, whatever it might be. I can't rank those countries. I can't do math on that information, but I know you're in a category of some kind. It's the least useful kind of measurement. I can ask you, again, what's your sex, male, female, whatever. I could rank it, but it's not useful. It doesn't mean anything. I can't do math on that information. I can ask you how many, well, that's not right. So the only thing I can do, the only kind of math that I can do is to count how many people say they were born in Quebec, how many people say they were born in Ontario. That's it. That's why it's the worst kind of measurement. It's also possibly the most common kind of measurement you get from people who don't understand numbers well. What I want you to do, like as this module unfolds, is when you read the newspaper, read like survey data, survey responses, and see the kinds of information they're collecting and ask yourself, is that how they should have asked the question? Is that useful? Is there a better way? Rather than, surveys always skew towards categorical and nominal variables that really aren't that useful. So that's nominal. The next is ordinal. Ordinal is a little better than nominal. It's not great. Ordinal means ordered. There's an order to it. Right? So a standard ordinal measurement would be how much pain are you feeling right now? 1, none. 2, some. 3, a lot. Okay? That's also called a Likert scale. You've heard of Likert scale before. I hate Likert scales from a statistician's point of view. No one knows how to analyze them well. Whenever a client comes to me, they've always got endless Likert scales in their day. I'm like, why do you do this? Because that's what they know, right? But it's not really useful. The problem with this approach is we can say that 1 is no pain, 2 is some pain, 3 is a lot of pain. What does 1.7 mean? We know it's somewhere between 1 and 2, but how far? Right? Also, the difference between no pain and some pain is different from the difference between some pain and a lot of pain. Right? So it's not so much this, it's this, then this. Right? So it's not consistent, it's not useful. So again, that reduces the amount of math that we can do. If I have this data, like a list of people who rank their pain that day on the scale, I can't do an average. I mean, you could, but it doesn't mean anything mathematically. Right? So I'm limited to what I can do. Averages do not make sense. Next is the interval measurement. Now the next two, interval and ratio, are very similar. Yes, sorry?
Is there an example of ordinal measurement besides HSS5902?
Sure, we can look at the number of doors in your house. Okay, so let's say, okay, number of rooms in your house. Okay, let's say your house has 7 rooms, and his house has 4 rooms, and her house has 12 rooms. Okay, so I can rank that. 12 is higher than 7, which is higher than 4, but the average number of rooms is, let's say it's 7.8. 7.8 rooms? What does that mean? Or 2.3 children? That doesn't mean anything. Okay. So now that example is a little better than the pain scale example in terms of how useful it is, because the difference between 1 room and 2 rooms is the same as the difference between 2 rooms and 3 rooms. Whereas the difference between no pain and some pain is not the same as some pain and a lot of pain. Okay, so ordinal comes in a variety of features. The idea is they're ranked, but then there's no value in between. Okay, that's the key part, no value in between. Of these last two, interval and ratio, they're very, very similar. The only difference is that the ratio measurement has a rational 0, and the interval measurement does not. Okay, a rational, what does that mean? It means that the 0 means something in the real world. If I tell you that it is 0 degrees Fahrenheit outside, what does that mean? It means it's cold, but it doesn't actually mean anything in terms of 0. If I tell you it's 0 degrees Celsius, well, okay, we can say that 0 is how we define the boiling point and freezing, the freezing point and melting point of water. But if I tell you it's 2 degrees in Winnipeg and 4 degrees in Saskatoon, does that mean Saskatoon is twice as hot as Winnipeg? No, they're almost the same. Okay? So suddenly, because that 0 doesn't have a real meaning in the real world, I can't do multiplication. On the other hand, if I say you are 2 feet tall, that person's 4 feet tall, is that person twice as tall as you? Yes, because 0 height means something in the real world. It all comes down to the meaning of the 0. So those interval measurements don't have a real 0. Temperature scales, except for the Kelvin, are all interval, because zeros don't mean anything. Oh, forget this note. This is from a textbook I used to use. I don't use it anymore. Okay. Ratio, on the other hand, is the thing that we care about. Ratio is everything. So all the math you learned in high school, is that a question? No. All the math you learned in high school was done on ratio measurements. So try when you can to use ratio measurements. Will this come up in what we do here today in this class? A little bit, not too much. I just want you to be aware these things exist, and sometimes you will see problems in your studies that are explained by just having chosen the wrong measurement. Okay. So at each measurement level, there's information gained and lost, right? High level scales are usually preferred. So you want to have a continuous measurement, not a categorical measurement, when you can. Okay. So here's a summary of how these things work. The kind of things you can do. With a nominal measurement, you can count how many people are in each group. With ordinal measurement, you can count. You can also rank how many are in each group. With interval, you can count, rank, and subtract. And with a ratio, you can do all this stuff. So it comes down to that. All right, moving on. I'm moving through a lot of topics fast. Okay, so stop me if anything gets really problematic. When we talk about statistics, there are 2 kinds of frequentist statistics. We mentioned frequentist and Bayesian. Under frequentist, there are 2 kinds: descriptive and inferential. Descriptive statistics is just describing what I have in front of me. So let's say you are my sample of students in the University of Ottawa. And I can say, well, the average age of this sample of students is 25 years. The number of females in this sample of 1, 2, 3 of 20 is 17, let's say. Right? I can describe things in my sample. If I'm attempting to use this sample to learn about the broader population, I'm inferring something. That's inferential statistics. Okay? So descriptive statistics relies upon a sample, which is you, in this case. Inferential statistics allows me to take the sample and infer things about a reference population. So in this case, the reference population will be all of the students in the University of Ottawa. So if I want to say, what is the average age of the students in Ottawa? I could possibly collect all 30,000 students and add up their ages, but that's a lot of work. It's better off if I get a representative sample, get your age, get the average, and do something with that number to allow me to estimate the average age. So this is what we are trying to do. This is what people think we're doing. So in elementary school, you do this, right? And newspapers do that. People, hello. You're welcome to join us. Look on her face. What? Right? So keep in mind that ultimately we're going to do math on our samples in order to learn things about a larger population. That's all we're here for. Otherwise, what's the point? Okay. Right? And we do this by using the laws of probability. So all the tests that we will be exploring use the laws of probability to manipulate information from the sample to learn about a greater population. Some of the terminology we use is statistic and parameter. The word statistic technically refers to information I get from my sample. The word parameter technically refers to the information I infer about the larger reference population. So if I want to know the average age of students in the University of Ottawa, and I take your average age to make that estimate, I've computed a statistic to infer a parameter, which is the average age of the University of Ottawa. And again, I'm repeating myself a lot here because these terms will pop up a lot. Yeah, no, yeah, no, no. What's wrong? Okay, let's see if we go through this example here. Okay. If I'm trying to measure how many calories a typical Toronto school children ingest, I cannot collect all of the diets of every school child in Toronto. I cannot do that. Instead, I will get a sample of Toronto school kids, and let's say I select 300 kids, right? And I compute their average caloric intake. That's a statistic. I massage that number using techniques I will show you to learn the average daily calories consumed by all the children in Toronto. That's the parameter. We use the statistic to estimate the parameter. It's a terminology thing, that's all. It's also a philosophical thing. You'll see how this unfolds, hopefully. Yes?
So like technically in this case, the numbers will be the same?
No. Okay, that's an important... this is what people get caught up on a lot. The numbers will not be the same. They'll be close. And when you do statistical testing, let's say you've collected data and you are wondering, hey, maybe I've discovered something new about the world based upon my data. What you're going to do is test your statistic to see how different it is from the expected parameter. And if it's really different, you conclude something special is going on here. This difference is statistically significant. Okay? At the end of today, you'll understand what that means. That's my goal for this morning, is for you to understand what that statement means in a second. Okay, so let's move on, and hopefully it'll become clear. Okay, so this is not a useful slide. It's just here because in your reading, you will learn about parametric tests and non-parametric tests. This drives me crazy. Just don't worry about what it means. It just means a parametric test is one that assumes there's an underlying distribution to the way the world unfolds. And a non-parametric test does not rely upon that. Don't worry about anything else here, okay? This will confuse you, but keep that in the back of your mind in case those words pop up. So, and keep this slide to be referenced in the future as you do your readings and you move forward in your career. Sometimes you want to be able to do these things. These are the kinds of tests you can apply. So commonly, let's say you want to compare two measurements from the same group. The first one. Let's say I want to figure out if the average age, or the average, here's one, good one. If the average mark of the midterm of this class is different from last year's. Now, I could just look at your average mark, look at last year's average mark. So your average mark is like 90, and last year's it was 89.9. Are they the same? They're different. They're pretty close, right? Are they different enough to warrant me to say, hey, they're really different? I use an independent samples t-test to determine if that difference is wide enough. Okay? Again, this slide here is just for you to have reference to later on as you do some data analysis. Okay. Before we get to answering that question, though, we've got to go over something called frequency distributions. A frequency distribution is how we organize our numbers. Okay. So you can organize it in terms of a table or a graph. Let's say I'm collecting the height of everybody in this room. And you are 6 foot tall, and you're 5 foot tall, and you're 4 feet tall, you're 6 foot tall. Suddenly, those first four people, I have 2 or 6 feet tall. So now all of a sudden, 6 feet is becoming common. And so you're 7 feet tall, and you're 4 foot tall. Now we've got 2 6-footers and 2 4-footers. Ah, those two are now competing. So adding up how frequently things occur is a frequency distribution. This is the essence of learning about statistical significance, is how frequently things occur. Because if I know how frequently things are meant to occur, and the thing that I find is actually not that frequent, maybe I can say my sample is very different from what is expected. My sample is special. On the other hand, if my sample is the thing that is frequently found, then my sample is not that special, and I move on. Okay? I fail to reject the null hypothesis, and I move on. This is why we're doing this. So when we're doing frequency distributions, we just count up how many things there are. So for example, let's say we have 10 people, and these are their ages, 17, 26, 33, etc. Right? So, and we're going to categorize them by age group, 0 to 25, 26 to 45, etc. Right? So there are 4 people who are between 0 and 25. There are 4 people who are between 26 and 45, and 2 people over 45. So the relative frequency, 4 out of those 10 is 40%, right? And I can add them up as well, cumulative frequency, etc. That's all these words mean. The important part is here, is 40% are this age, 40% are that age, and 20% are that age. That's a frequency distribution. Very simple. What can I do with that? Well, I can group them differently. Here's ages of people, right? So we've got a bunch of people. 1 person is 98 pounds, 2 people are 102 pounds, 0 people are 101 pounds. I can look at it that way, or I can group my pounds and say 75 to 100 pounds, or have 6 people. Right? I can make the groups even bigger. I can say 75 to 125 pounds. There are 21 people in that group. So depending on how I define my groups, the frequencies change. Hopefully this is triggering some memory now as you think about histograms. Because how we define histograms, if we change the groupings, things change. Okay? So I could report each person's individual weight, each person's individual age, each person's individual height. That's cumbersome if I've got several hundred people. Or I can start to group them, kind of like we did earlier with moving from continuous to categorical. We're losing wisdom, but we're presenting it in a convenient fashion now. So histograms are a visual way to show the same thing. Histogram looks like this. So this is heart rate data. So there's like 1 person's got 55 beats per minute, 3 people have 57 beats per minute, and the biggest one is 12 people have 66 beats per minute. So right away, I can look at that distribution, and I know what the most common heart rate in this population is. It's 55, or it's whatever this is. 66, right? So if you have 54 beats per minute, you're like, oh my God, I'm much lower than most people. I'm unusual. If on the other hand, you have 64, well, I'm close to being most people. I'm not unusual. Again, the narrative is, how different is my sample, my test result, my observation from what is expected? Okay. So histograms allow us to visually portray what is expected. And what is expected is essentially what we've observed in other populations. That's the essence of how we're going to tell how something is statistically significant, is how different your observation is from what is expected. When we look at histograms, or graphs in general, there are three characteristics we can measure about those graphs: modality, symmetry, and kurtosis. I know it's a lot of stuff I'm throwing at you. I got to get through this basic stuff before we can do the even less fun stuff, which is okay. So these three characteristics are useful in assessing right away your sample. So let's say you've collected data for your study, and you can present your data in a graph form. That's fantastic. Let's say your study's on, heart rate. That's fine. So these three characteristics are defined this way. Modality is how many peaks there are in a histogram. Okay? If it's one peak, it's unimodal. If it's two peaks, it's bimodal. If it's more than two, it's multimodal, et cetera, et cetera, et cetera. Here's unimodal, bimodal. Okay? How is this useful? I'll show you how it's useful, especially in a health sciences context. Okay? Do you know how we test for tuberculosis? Has anyone ever had a tuberculosis test? Yeah, how does it work? You know?
Just check the fetus.
That's exactly right. What are they looking for? Do you know what they're looking for? They're looking for a reaction called an induration. This is actually a friend of mine, her TB test. She was tested positive. Okay? They're looking for whether or not the skin raises up by a certain width. That's called an induration reaction. If it's above a certain number of millimeters, we call that a positive tuberculosis test. Now, it is possible to just have an allergic reaction to the pricking of the needle and get a small induration. That's not tuberculosis. The question is, how do we know where to draw that cutoff between an allergic reaction and an actual tuberculosis induration? How do we make that clinical designation? This is how. You do it to a lot of people, and you collect all the data, and you graph the data in a histogram, right? This is real data, by the way. So all this is just an allergic reaction. This is tuberculosis. So we know if your personal induration is over 9 millimeters, then we conclude you probably have tuberculosis, and we send you out for further testing. If your induration is less than 3, it's an allergic reaction. If you got nothing, you're probably fine too. Okay? Now that may horrify you. Like, really? Clinical decisions are made upon these averages? Yes. That's how it's done. This is why we do this stuff. So this multimodal distribution leads directly to clinical application. Let's say it's not as convenient as a multimodal distribution. What about a unimodal distribution? What is this? This is systolic blood pressure. What is a normal blood pressure clinically? 120/80, exactly. So the systolic is the 120. We say 120 is normal. Why? Because that's what most people have. That's the only reason. Doesn't mean it's healthy. It's just typical. Okay? So when we test your 120, we're saying you are a typical blood pressure of 120. It doesn't mean you're healthy blood pressure. So there's an assumption in this case that typicalness means normal. Okay? So again, this is why we do this stuff. Distributions lead to clinical relevance and direct application in the real world. That's why it's important. Okay. So symmetry, that's modality. Symmetry is how equal they are in the center. Okay. So if something is non-symmetric, we say they're skewed. If there's a tail here and the tail points in the positive direction, that's a positive skew. If it points in the negative direction, that's a negative skew. Why is that important? Because it's a quick and easy way to tell if there are outliers in your data that are pulling information one direction or another. Okay? Kurtosis is the one you probably never heard of before. Kurtosis is how flat or how sharp the distribution is. So if it's leptokurtic, it's thin and tall. If it's platykurtic, like a platypus, it's flat. If it's mesokurtic, it's something in between. Okay? So it looks like this. A leptokurtic is high, a platykurtic is flat. And SPSS and other stats packages will measure this for you if you want. It'll give you a number. Your kurtosis index is this. Your skewness index is that, if these things matter to you. So this is important if, when you collect data, you need to understand your data set. And one of the first things to do is look at your data in terms of frequency distributions. Let's say you've got age data, you've done a survey of people and, like everyone's average of 25. There's one outlier who's 98 years old, and you've surveyed the student population, one old person that showed up at class. That's fantastic. But you may need to remove that person if it's not relevant for your research question. Okay? So this is the first step towards cleaning your data. The next couple of slides, I'll show you how to do this in SPSS. I won't go through this right now, but on your own, you can go through this and just figure out how to access these things in SPSS. Okay. Moving on. Whew, a lot of stuff. If we have a bunch of data now, let's say data on age, the age of students in the University of Ottawa. Now you know you can graph it now. You can look for symmetry, you can look for kurtosis, you can look for skewness. Let's say I ask you, what is the typical age of people in this class? What would you tell me? How would you go about figuring that out? What is the typical age of people in this class? What would you do?
Yeah, and then you average it out.
Average it out, okay. Average, mean, is a measurement of typicalness. It's not always the best measurement of typicalness. I showed you earlier that some scales, like the ordinal scale, you can't do averages on. It doesn't make any sense to have the average pain. Okay, I can't do average average province of birth, that sort of thing. So we have several different measurements of typicalness. As your career moves forward, you will be asked, what is the typical this, the typical that? Give me an estimate. This is what central tendency is. It's, okay, I see. So usually the mean, the average, is the thing that is the typical, like the average age of this class, the mean age is the typical one. But if there's an outlier, if it's like a 4-year-old in this class or 100 years old, they're going to pull that average this way, and it's not really typical anymore, is it? Okay? So if it's, let's say you're all 25, and let's say I'm 90, and we take the average of this class, suddenly the average is something in the 60s. Is that really the typical age of this class, 60? No, it isn't. One dude has pulled everything this way. Right? So the mean is not the right measurement. So we need other measurements of central tendency, of typicalness. And we tend to have 3 of them. Mode, median, mean. And I'm sure you're used to these words already. These are elementary school stuff. Okay, but we'll review it anyway. We care about them because we need a way to communicate the basic information about our sample. So the mode is the most common number. Here is a way of depicting modality again. So this is the age of 7 people. Right? 2 of them are 27. One's 26, one's 28, and so forth. The most common one is therefore 27. The typical age in this group is therefore 27, according to mode. Straightforward. Median is the one that's in the middle. So if I were to rank these ages, right, the middle one is going to be 26. We write 27 and 28, right, because there's an equal number below it as above it. Same data set, but different measurements of typicalness now. And the mean, you know how to do that. You just add them all up and divide by the total. We get 28.3. They're all similar, 27, 28, and 28.3. Okay? Which one do you choose? It depends on the story you are telling. It depends on the nature of the data as well. If the data is ordinal, if it's ranked, median makes more sense. If it's a ratio level, mean makes more sense. Mode makes sense if I'm counting up the number of people who were born in the various provinces. 3 of you are born in Ontario, 6 of you are born in Quebec, 1 of you is born in Alberta. Now, Quebec is the most common one, so the mode is the typical measurement. So it matters. Right? So the symbols here you've probably seen before. X bar, a bar on top, means average, means mean. Right? That's the statistic, the measurement in the sample. Remember, statistic means the measurement in the sample. In the population, the parameter, the thing I'm trying to infer about, we use the Greek letter mu. Okay. And Outside of this class, you'll probably never do this ever again. But if you ever read a statistics textbook, that's what this means. Mu means average in the parameter. Okay. So here's how these things look when they're skewed. In a perfectly symmetrical normal distribution, the mode, median, mean should be the same. So even without being able to do a graphing of your data, you can look at your Excel file of all your data and compute the mean, the median, and the mode. And if they're all the same, automatically you know this thing is perfectly symmetrical. On the other hand, if it's negatively skewed, the mean and the median start moving towards the left of the mode. If it's positively skewed, the mean moves towards the right of those things. So, yes?
On the previous slide,
Yep.
so the population means the mu hasn't been measured, it's been assumed based on the sample, right?
That's right. Yeah, right. Exactly right. We never measure the mu, right? We always assume, because we can never know, it's theoretical. Okay. So variability. So we measure now central tendency, typicalness. Now the question is, how wide is your distribution? How varied is it? I mentioned earlier, if we got a bunch of 25-year-olds and one 60-year-old, then there's some variability, there's some width in my data that may give me some problems. How do we measure this width? That's called variability. Okay? And there are different ways of measuring variability. There are 4 ways that are typical: range, interquartile range, standard deviation, and variance. I'm not going to go through all of these. So I want you to be aware of them. You may read about them. Increasingly, if you read clinical trials, they will talk about interquartile ranges. And what the hell is that? That's a measurement of how wide the data is. Range is very simple. It's the difference between the highest value and the lowest value. But we'll talk about this, standard deviation. This is just the square of that. So the ways in which the different levels of measurement play out in typicalness and variability is this way. If your data is nominal, that is, if I'm measuring which country you're born in, whatever it might be, I can only really measure the mode, how frequently people are born in Quebec, how frequently they're born in Ontario. And there is no way to measure the width. There's nothing available to us. If the data is ordinal, Likert scales, on a scale of 1 to 7, how do you feel today? The best way to measure typicalness is the median, because we can't do means. And if I'm measuring the width, the range is a good option for that. I can say, well, 60-year-old versus a 20-year-old, whoever it might be. And this thing called IQR, which I will not define for you. Yes?
For the nominal one, I guess you wouldn't be dichotomizing them because it wouldn't be to 1 or 2, but if you said that you wanted to find out how many people were not born in a certain country, so it would still be nominal because you would be looking.
Yeah.
Couldn't you then, in some way convert to a numerical kind of way to then have a standard deviation? Or to then have a variability?
No, because you can't gain information that doesn't exist.
Okay.
Right? I mean, you might be able to fake it, but it wouldn't mean anything.
Mm-hmm.
Right? I mean, thinking outside the box, though, it's good. And the last, of course, these last 2 measurements, the pure numbers, you can do all of them. The mean is the best way to do it, and standard deviation. So we're going to talk about standard deviation now because it's an important concept. So standard deviation tells us, on average, how much the data in your data set vary from the mean. So the mean is our measurement of typicalness. How different are each of these from the mean, on average? Okay? And they're based on deviation scores. A deviation is, again, how much each person's information deviates from the mean. I'll give you an example. By the way, an SPSS, you just click on these things to get it. Right. Standard deviation is important, and it confuses a lot of people. But in this distribution here, the number of standard deviations away from the mean means something important. 1 standard deviation from the mean is about 34%. So 1 on either side is like 68%. 2 on either side is like 95%. By the time you got 3 standard deviations on both sides, you've got 99% of everybody. Okay? So you'll read sometimes like we sampled X people plus 2 standard deviations of the population. That means they covered 95% of the population. Okay. So we'll get back to that in a second because it's an important concept. So let's say we are weighing 10 students and we get their weight in pounds, 110 pounds, 120 pounds, etc. What's the mean weight? Add them all up, divide by 10, you get 150. That's their mean weight. Okay. Now, the lightest person, the deviation score is the mean minus 40. The lightest person is 150 minus 40, 110. The heaviest person, the weight is the mean plus 40. Okay. A deviation now is going to be the amount that each one has diverted from the mean. For that first one, it's minus 40. For the highest one, it's plus 40. The standard deviation is just the typical deviation. That's all it means. Okay? So it's a measurement of how typical the data of deviations is. So let's go through all of them. This one, the deviation score is going to be minus 40, right? Because it's minus 40 away from 150. The next one is going to be minus 30. Next one is minus 20, etc., etc. This one is 0. They're exactly the same as the mean. And so forth. If I add them all up, I'm always going to get 0. Because the amount of things deviate from the mean adds up to 0. That's the way it works. That doesn't help me any. So the way in statistics and mathematics in general, you get rid of negative numbers, because the negative numbers, that's what's causing them to cancel out. The way you get rid of negative numbers is to square them, and you'll see this all the time. We take the square of things just to get rid of the negative numbers. Okay. So here it goes. In other words, the standard deviation is going to be the sum of all the squares divided by that. Okay, I know I'm talking fast here, sorry. We're looking for the typical deviation. I said earlier, one measurement of typicalness is the mean. So we take all the deviations and we take the mean of that. Now, because there's some negative deviations and some positive ones, if I add them all up, I get 0. It doesn't help me. If I square them and add them up, now I've got something. I can take the average of that now. Now, why isn't it n and not n minus 1? I don't want to get too deep into that. So in statistics, we have this thing called degrees of freedom that nobody understands. What it really says is, how do I put this? We lose information when we go one step above what we expect. I'm not making any sense, I know. Trust me on this. When we're dealing with samples, we take something away from the denominator just to make it a little more precise. If this was a parameter estimate, it would be an n. Just trust me, that's the equation for it. And we can debate it later when I've had more sleep, because it's more complicated than that. So here's an example again. Same example. 100 weight. We take the deviation scores. We square the deviations. Minus 40 squared is 1600. Minus 30 is 900. Add them all up. Take the average under the root sign, and we get 25.82. What does that mean? It means that's the standard or the typical distance from the mean that each of these data points has. One data point was 40 away, one was 10 away, one was 0 away, but the average distance is 25.8. Okay? The bigger the standard deviation, the wider the data, the more dispersed it is. The smaller standard deviation, the more compact it is. That's all it means. Okay? And the notation looks like this. It's the Greek letter sigma is the parameter. We are trying to measure the parameter. We use the S for the sample, the statistic. The statistic estimates the parameter. When I square the standard deviation, I get variance. Just get that terminology straight in your head. So how is this important? It's important because it tells us, on average, how wide things are. It also allows us to standardize distributions. As I mentioned, 3 standard deviations away from the mean gives me 99% of the distribution. That'll become relevant in a second. And by the way, you get this in SPSS by going here and here and here. Okay. Now, we've talked about standard deviation, we've talked about central tendency, we've talked about frequency distributions. That takes us to, yes, question?
So, the standard deviation only used when the mean is representative of the typical example?
Oh, sorry, I didn't hear you. You're standing up.
So, we only use the standard
Yes. Yes. No. I mean, you could use it is a description of the data set. If the data set is made of ordinal measurements, it may not be useful. Okay. Most of the data you'll be dealing with will be using means, though. So the normal distribution, the word normal confuses people. In this case, it's a stupid word, and I wish they'd chosen a better word. Normal, capital N normal, is a label. It's the name of a special distribution, a special curve. Also called the bell curve, also called the Gaussian curve, the most important curve in the history of mathematics. And it has a wonderful history behind it. Okay? So it's called the Gaussian because one of its discoverers was Gauss, the greatest mathematician who ever lived. And I got a lot of Gauss stories to tell you if we have time, but we don't have time, so screw that. And one of the reasons, probably the most important reason that it's so important, is that everything in the world follows the normal distribution. Every human characteristic, not everyone, but almost every human characteristic, every human experience follows it. And I'll show you why it's magic in a second. Because in my mind it is magical, and it's useful that way. So it begins with a coin flip. If I flip a coin once, I get a head or I get a tail. If I flip it 2 times, I either get 2 heads, 2 tails, a head and a tail, or a tail and a head. Okay? So it's kind of random. So the first one here shows me what I get with 2 flips. I either get 2 heads, head and a tail, tail and a head, or 2 tails. In other words, how many times do I get no heads? Once, right? One time I get no heads. How many times do I get 1 head? Well, 1, or at least 1 head. 1, 2, and 3, right? So it's somewhat 3. How many times do I get 2 heads? Just once. In other words, if I were to graph the number of times I get at least a head, it looks like that. Let's say I flipped a coin 4 times. Well, I would get more data. How many times do I get no heads at all? Just once. How many times do I get all heads? Just once. How many times do I get at least 1 head? A quarter of the time. How many times do I get at least 2 heads? Like 40% of the time. Look at that. The distribution starts looking like a hump. If I use 12 flips, it starts looking that way. Right? In other words, by the time I get 12 flips, I have this magical normal distribution. That's amazing. Right? A coin flip gives me a curve. That's amazing. So the history of this is fascinating. We think it was first published in 1733 by De Moivre, and De Moivre was a gambler, a professional gambler. He was a consultant to the royalty of Europe, advised them how to win in gambling. But he was doing all this probability testing. I can produce a normal curve every time I do this. Pearson wrote about it in 24. Gauss, the greatest mathematician of all time, pointed out that, actually I did this back in 1809, right? And he did it when his students were doing coin flip experiments, and they kept finding this curve. He says, why can't you do this right and get me a regular? And he did it too. Wow, there's something magical is happening here. This curve keeps coming up. In other words, it has an important place in history, and it's the foundation for almost everything that we do in frequentist statistics. That's De Moivre, by the way, who's an ugly, ugly man. Look at that. It's hideous. Okay. One of the reasons that the normal distribution is so important is because of something called the central limit theorem. Don't worry about the details of the slide. I'm a lazy guy, so what I've done is I've copied these slides from my other stats classes. So it's got some extra information that maybe you don't need. So just remember what I'm saying. One of the magical aspects of the normal distribution is this thing called the central limit theorem. And the central limit theorem simply says that no matter what shape or what the characteristics of that first experiment is, if you do it enough times, the outcome starts looking like this magical curve. A coin flip, 1, 2, 1, 2, 1, 2, it starts looking like this magical curve. And we'll see how this manifests in a second. Okay, first of all, the normal distribution, the bell curve, it allows us to convert frequency distributions to probability and p-values. I'll show that in a second. Right? It has a bell-shaped curve and it's symmetrical. and it's symmetrical around the mean, so that center is the mean. Okay? The standard normal distribution, this thing we call the standard, has a mean of 0 and the standard deviation is 1. Right? So we use the standard as a way to compare other things to it, and you'll see why that is hopefully in a second. As I mentioned earlier, around the standard, 68% is 2 standard deviations, and about 95% is, 68% is 1 standard deviation, and 95% is 2 standard deviations. Okay, exactly what I just said. The mean plus or minus 1 standard deviation covers about 67%. The mean plus or minus 2 standard deviations covers about 95%, et cetera, et cetera, et cetera. The number 1.96 will come up a lot in your readings if you haven't seen it already. If you've done Z-scores and t-tests and things like that, you've probably seen 1.96. Why is 1.96 so important? Because exactly 1.96 standard deviations away from the mean on both sides gives us 95% of everything. 2 standard deviations gives us 95 point something, but exactly 95% of everything is covered in 1.96. So that number will pop up in your computations a lot. If that bothers you, don't worry about it. It doesn't affect anything. It's just there for your erudition so you understand where it comes from. Okay? You probably heard about 95% confidence intervals. Remember that stuff? Right? That comes from this. 95% confidence intervals are saying essentially that if I did the experiment a billion times, most of the time it'll fall within 1.96 standard deviations of the mean. That's all it means. Okay. Here's how it works. This is actual data. This is the height of adult men and adult women in North America. Okay. So if I look just at the women, it's pretty much a normal curve. Just at the men, it's pretty much a normal curve. You've probably heard people say like the variation within the population is greater than between the populations, so they dismiss it as a result. All it means is that, yeah, the width of female height is quite large. The width of male heights is quite large too, but the average is distinct. Men on average are taller than women. Big surprise. Okay? So you see there, that's how that works. But there's a large number of people who are interchangeable almost in terms of height. I'm average female height. I'm proud of that. Now it gets even more complicated and a little controversial. This is a measurement of aggression divided by sex. So the blue is female and the red is male. Okay? So both men and women have the same variability in aggression. We have aggressive women, we have passive women. We have aggressive men, we have passive men. On average, men are slightly more aggressive than women. Okay? So but the important part here is the tail. So right about here is where the aggression gets so bad that they become criminals, right? Violent people. So if we just look at the criminal population, they're almost all men. And these numbers actually correspond almost precisely to our prison population. So one explanation for the gender distinction in prison populations is the distributions of the aggression trait among men and women. They're almost the same, but in the extreme tails, there are more men. And there are more timid women as well. Right? So that's how that works. Here's how it gets even more controversial. I'm just reporting data. I'm not giving you conclusions. So I don't want any tweets saying, Dr. Deonandan said this. No, I'm just reporting data. This is IQ. IQ is very interesting. Whether or not you believe IQ measures anything useful or not, that's another story entirely. But the red is female IQ and the blue is male IQ. And this data is repeated pretty much in every population around the world. Average IQ for both sexes is the same. That's repeated endlessly. But it's the tails that matter. Look at the distributions. The females have a more tighter leptocurtic distribution, and the males have a platocurtic, wider distribution. So while the average IQ is the same for both, there are more men in the dunce class. There are also more men in the genius class. Some people make this argument, this is why there are more male Nobel Prize winners. Some people say, I'm not saying that, I'm just saying that's part of the argument. It's also why there are more men who are technically mentally retarded. So if you were to use this approach to explore population health dynamics, it can produce some insights and some controversies. Okay, so again, I'm not telling you what to think. I'm just showing you some data. All right, so let's go back to IQ. IQ is interesting. And this shows us the magic of normal distribution. We know, this is true, the mean IQ is 100. It always is 100. We know this because every year we reset the test so that the mean is 100. And the standard deviation is 15. By the way, we reset the test every year to be 100 because every year it gets higher than 100. People are getting smarter. This is called the Flynn effect. Right? I want you to think about this. This is byproducts of data analysis. Every year people seem to be scoring higher on average in the IQ test. So is the human race actually getting smarter, or is something else happening? Think about that. We'll talk about it next class, right? So anyway, we have some theories. Oh, right.
What did you say the effect was?
The Flynn effect, F-L-Y-N-N. It's curious. Okay, so accept this on faith, that the mean IQ is 100 and the standard deviation is 15. Okay? Now let's say we take a random selection of 25 kids from a downtown school and measure their IQs. What is their mean IQ going to be? These 25 kids. Give me the wrong answer, come on. Is it going to be 100? It probably is not going to be 100. Okay? It's going to be something different than 100. Why? Because there's going to be some sampling error. You might get 101.6, you might be 99, might be a number of things. Because 25 kids, people belong in our class? Look around here. Hey there. Oh, are we on already? Oh, damn. Okay, we're done. Oh, okay, crap. All right, no problem. All right. I'm going to get something good here. Okay. I'll say but this. It's if you were to take 1 billion samples of 25 kids and take their averages, this was 99, 110, 115, 58, and graph these averages, you get that. That's the magic of normal distribution. It isn't that your sample is normal. It's the distribution of all of the samples. And that's a magical thing that I want to have more time to talk about, but I can't. So we'll save this for later. Okay, see you guys later. For some reason I thought we had it at 10:30.
It's okay, we're all late.